Hello, everyone. Someone asked for a little bit more of an in-depth explanation of the AGS clock syncing. So, unlike the Disky, it is impossible for the AGS to receive direct uplinks from the ground. So, syncing the clock was required to be done manually and is done slightly differently than with the Disky. With the Disky, you're allowed to get it really close. And then any sort of remainder would be fixed via a later clock sync. But with the eggs, it's pretty important to get it as close as physically possible. So we'll go through how this works. So to start off, we can pull up verb 16, noun 65. And we can see we have a time readout. We'll go ahead and pause. So the register 1 displaying in hours, while register 2 displays in minutes, and register 3 actually displays in seconds and centiseconds. Centiseconds is a lot like cents in your currency. For example, in the dollar format, this could be read as $22.38. Obviously here it's in seconds, so this is 22 seconds and 38 centiseconds, represented with a decimal, which is not actually there because these computers don't support decimals. The problem is you actually need to work out a little bit of math. Unlike the Disky, the eggs can only display one data value at a time. So we'll go over the eggs display. The eggs display is in decimal time. This means that the eggs is actually in minutes and centiminutes. That is a base 100 unit for minutes. So the minute slots would occupy 1, 2, 3, and 4, and the centiminute would occupy position 5. To sync the clocks, we need to take a look at our bias time for the mission. In our mission pad, we're required to have a bias time of 90 hours. So to start off with, we'll simply take 91 and subtract 90 from that. We're left with 1 hour, 42 minutes, 41.38 seconds. Now we simply need to take registers 1 and 3 and convert them into a register 2 format. Since the eggs is in minutes and centiminutes, we basically just need to move register 1 down to register 2 and register 3 up to register 2. So to start, we'll convert hours into minutes. We'll take 1 hour and we'll multiply that by 60 and we'll add that to 42. So our register 2 readout would now theoretically be 102. Moving the seconds up into minutes can be quite tricky, since the seconds, as you know, there's 60 seconds per minute, which means that seconds are actually sexagesimal, and we're looking for something which is in base 100. So our seconds are in base 60, and we're looking for something that's in base 100. But that's not really a problem. We can represent an elapsed time up to 60 as a percentage out of 100, say like 90%, convert that into a decimal, 0.9, and that is now in the base 100 format. So let's say 30 seconds is half of 60. That's 50%. Represented as a decimal, that's 0.5. And we've done that conversion. We can represent that decimal as a fraction to get this conversion done. So we would simply take 41.38 and divide that by 60 to get a decimal. We get 0.689. We will round that up to 0.7 because, as you remember, position 5 is the only position available for centiminutes. So we cannot have more than 2 positional values inserted. Therefore, all values must be rounded to the nearest decimal. So our new readout would actually read as a register 2 readout, theoretically equivalent to 102.7. And that could be what we inserted into the eggs. And the only problem is that it takes time for us to do the conversion, and it takes time for us to insert that into the abort guidance system. So we actually have to select a time that's in the future. Let's go with 1 hour, 43 minutes, and 30.38 seconds. Doing the conversion, we'll simply add 43 to 60. That gets us 103. And then we'll take 30.38 and divide that by 60, getting us 0.51. And since the 1 is less than 5, we'll go ahead and round that down to a 0, equivalently just throwing the 1 out. For anything 5 and above, you'll round it up to 0.6. So on the computer, we'll simply do 377 for the time plus 0.103 decimal 5. And now we wait for this clock to get as close as possible to that time. We'll go ahead and give it just a little bit of time skip. So 5, 4, 3, 2, 1, enter. And that syncs the clock. After this point, you'll need to do a downlink between the eggs and the diski. And we could see we did initially calculate with a bias time of 90 hours. Like that. However, there is a little bit of delay, between your eyes seeing something and you hitting the enter button on the eggs. So there is actually a slight, maybe milliseconds delay of reaction time that you need to account for. Therefore, our bias time, because we're not allowed to interface directly with the eggs from the ground and correct that very small reaction time as we were during the diski clock sync, we actually need to have the ground calculate the deviation. And this is called the K factor. We'll talk more about that during the RTCC tutorials, but for now, we'll just go ahead and nab a K factor. So here we go, our K factor, and this would normally be read up to you from the ground. We are actually slow by 0.73 centiseconds. So this would be our K factor. And now, going forward, instead of updating the AGS clock, the computer will just take this new bias time, factoring in our own delay and our own human reflexes, and will modify the downlinking data, factoring in the slight 0.73 second delay, and downlink that data to the eggs. So the eggs will always run in its time. The computer will be what is calculating that deviation from that 90-hour bias. Hope that answers some of your questions. Thank you.